is visible?
Yes, sir, but
yeah, screen is visible.
yes, sir.
Okay, thank you.
But it has to be it has to be in the center. There is a slight is it visible to everyone?
Yes, yes.
Yes,
It's visible.
Okay.
Slide mode only.
Yeah.
Yes, yes. It is slide mode only.
Fine. So today's topic for my lecture is cyclic behavior of geomaterials. Let us see what I want to show, some of the glimpses of work on geomaterials under cyclic loading, which I wanted to share with the audience today. So we'll study a few natural and modified geomaterials, how they behave under cyclic loading. What are the difficulties associated with these materials? We can say all good things, but what are the bad things about this? How to measure their compacted density? One of the apparently very simple question, but it's I'll show you why it is one of the challenge in this kind of study. What about the static strength, liquefaction hazards? Then can we model them, or let's say at least approximately whether we can try to model them to some extent? So we start with natural cement treated marine clay, simple one, start first. You may wonder why we need cement treated marine clay to understand the cyclic behavior. Actually, there is a long story. I just summarized that coastal terrains in most of the countries are thick and thin with marine clay deposits. All we know that our eastern coast, western coast in India is full of marine clay deposits, and they are generally characterized by the high compressibility. So the settlement is the problem. Now, often we add a lot of additives to increase or enhance the strength characteristics, right? Now, till certain level, I mean, till like early 2000, there was an idea that if you improve the ground, particularly if you use the cement treated ground, like the one that I am showing here in the picture, that in Japan, it's very good. I mean, there is no problem if you treat in the with cement. Now, this particular figure, you see that's this untreated ground, and there was a pavement, and there was a kind of a sloping structure towards the sea, which got damaged during an earthquake in early 2000. Now, after that, they did that cement treatment. I mean, deep soil mixing columns, and then they created the entire thing again, and they thought that it is fine. But what happened is in 2011 during Fukushima earthquake, this entire pavement collapsed again, and there is a kind of a 45-degree failure plane developed in this deep cement mix columns. So that's where we started. Now, before going into cement treated soil, we thought, like, let us see how the cyclic soil behavior is. It's a degradation of soft clays during cyclic loading, usually very nicely documented by the researchers from the US West Coast. Started with Idris long back in 1978 with Banerjee. It says that it has nonlinear stress-strain relationship. Even at the very small strain, it is nonlinear. At the same time, stiffness degrades with cycle. Overall, what understanding is that the shear modulus degrades with a progressive increase in the shear strain, whereas damping ratio increases with the progressive increase of the strain amplitude. I mean, obvious. I mean, there is no rocket science involved. You make it the material softer, you enjoy more damping. But as you make the material softer, the bearing capacity become a concern. Now, to study this entire regime, so what I want to highlight here is there are three regimes clearly. One is elastic regime, where there is no degradation so far. I mean, more or less that stiffness remains same. And then there is a limited plasticity regime, I wanted to call it. It's a nonlinear started, but interestingly, the modulus is reducing. And then it goes to elastoplastic regime. To understand all this, you have to have a different type of testing. So started with cyclic triaxial test, which is generally good for the higher strength. Bender element test, which is generally good for very, very small strain. And in between, you have resonant column, which is pretty good in medium strain range. So if you have all these three, you will get a full spectrum of the shear modulus and damping behavior of a soil. Now, this is a resonant column torsion shear setup at IIT Madras Advanced Soil Testing Lab. This is our triaxial. Again, we have a new one as well. We have a Bender element as well. Now, in experimental program, we started with the Ennore marine clay, and where we mix the soil with the controlled amount of cement, and cement content varies different. I mean, here I am showing the results for 5 different cement contents. Of course, 0 means there is no cement added to it. And then varying frequency, cyclic strain amplitude, number of cycles I am fixed at 100, and then 3 different confining strains. First, the benchmarking, we check that whether our understanding is correct. We increase the confining pressure. Obviously, we expected the shear modulus, the maximum shear modulus increases, as well as if you increase the cement content, we saw that the maximum shear modulus increases. Same thing we have seen with the shearing stress. So this is not unexpected. This is expected, but this gives us a confidence about the preparation of the soil. Now, overall, when we do the we plot the hysteresis stress strain behavior, derivative stress versus shear strain, and we saw that it's clearly the cement treated soil also, like a natural clay, has a degrading nature. However, this degradation, as we use the IGC model, we can say that the cement treated soil degrades lower than the natural marine clay. So this is the degradation level. The red line is for the natural soil, natural clay, but the black line indicates the cement treated clay. Now it shows that cement need a much stronger strain level to break the bond or break the pozzolanic matters to reduce the stiffness. So which is good, which is not bad. But the thing that we have to note here is it's not the zero degradation. That means still, even if it is a cement treated clay, still degradation persists. So assumption that there is no degradation of stiffness with cyclic loading for cement treated sample is not valid. So we did some parametric study based on our experiments. In fact, we did a 3-dimensional thing because the factors, the frequency, strain range, cement content, all those things are kind of mutually interrelated. So and then we plotted this together, and then one of the key thing we understood here is pore pressure generation is very high at low loading frequency, which is kind of a counterintuitive, if you ask me, because we thought that, okay, if you have a very fast rate of loading, pore pressure development should be higher, but it's contrary. If you have a low frequency loading, so the load is sustained over the soil for longer time, so then the development of the pore pressure is more significant. Similarly, we repeated this thing for different confining pressure, different cement contents, for damping ratio and other thing. Then we started forming an analytical model. Now this is our idealized hysteresis loop. We put a hyperbolic backbone curve to this stress strain model. Then the unloading, reloading behavior, we try with the meshing rules, which is quite well known nowadays. And then stiffness degradation, we followed the IGC degradation concept. Now with that, we come up with our predicted hyperbolic hysteretic model shear modulus degradation curve, and we see that modulus degradation line is in line with not only our results are discrete black points, as well as if you take the points or the lines from the literature, our thing is quite nicely fall in between. So this gives us a confidence about our proposed model. So then we started with the degradation performance, cyclic degradation performance, check. And we saw that cyclic degradation is the function of strain, plasticity index, over consolidation ratio, and the frequency. And we compare with our results with other people results, all are quite same or quite satisfactory. Same thing we repeated for the cement treated clay as well. And again, we got the satisfactory comparison. Now, what about the contaminated soil? Like many cases, natural soil get contaminated with some leachate actions or something. Now we try to do that. We try to saturate the samples with a certain controlled proportion of sodium chloride. We have done with calcium chloride also, but I'm not showing the results. And then we compared with distilled water. And interestingly, we see that it's a contaminated soil degrades much faster, much more. Shear modulus degradation is much more significant compared to the normal distilled water saturated samples. And then we try to include that in our constitutive model. And we introduced a factor, we call it pore fluid concentration factor. And that this C is the concentration of the pore fluid comes into the picture. And then again, we compared with different level of pore fluid concentration. And we got quite satisfactory. I am not saying that these are the 100%, but those who are working in cyclic behavior, they know that the getting cyclic model, constitutive model, and to match exact, it's almost impossible. So now I go to the final part of my lecture is the particulate rubber sand mixture. So with cement and clay, we got a quite satisfactory results. So now, what about if you have a more coarser material like particulate rubber sand mixture? So the material is more or less uniformly graded, as you can see. We have tested with fly ash also, but I am not showing the fly ash results at this point. Here it's more like a rubber and sand. Its rubber sizes is 2 millimeter down. We maintain it. We had basically we use the cycle tires from the IIT campus, and then we kind of grinded it in a mechanical grinder and maintain the size 2 millimeter down. Rubber content varies 10, 30, 50%. Actually, we varied a large range, but still we are showing these three particular cases. And that's where the first thing comes. How to estimate the density? Well, we started with the conventional vibratory table method, but what happened is that density of the we saw that density of the mixture increases with if you have a larger surcharge in the vibratory table container, then density increases. On top of that, density of the mixture reduced because of the rebound. So immediately you remove the surcharge, there is an elastic rebound happens. So we lose the density which we estimated. So then we thought that, okay, Proctor and mini compaction method proposed by Sridhar and Srivapulaya in 2005 was found to be suitable. And we did that extensively. And we saw that, okay, these are the particular method because there is it has to be a low energy type of compaction. And then, of course, direct shear tests used for shear strength estimations. Now, one of the major problem of these mixtures is definitely you will get a lower angle of friction compared to the pure sand. So let's say I want you to highlight please notice these green points. So this zero, the starting point 0 rubber content means it's purely sand. Then we go for the 10%, then it is 30%, and then 50%, and we are done for the 100%. And you can see the friction angle reduces quite significantly, and it's a very sharp reduction. So that means one of the major challenge here is the static stability. So that means you see the static strength. Obviously, we did some triaxial test also with particularly this kind of material, and we have seen that you see this is the typically for the R0. R0 indicates pure sand. R100 is the pure rubber, and actually R10, R30, R50 are all falls in between. So the strength is a big problem. So it's again the modulus also we see that the steep decrease with increase in rubber content. Now, we did some microstructural study to understand why it is happening. It's happening because I'm not showing there due to the limitation of the time, but what we understood is here is the rubber surface has a tiny, it's a tiny undulations. The sand particle size is such that it's cannot be go and sit within rubber, those gaps in the rubber surface. Whereas if you add, in fact, our subsequent study, we've seen that if you add the fly ash, which is having finer particle size, actually help to bridge this gap. With fly ash, we could able to maintain certain level of angle of internal friction. Now, static strength control of settlement is a big problem if you want to use this material for your purpose of construction, particularly if you think of backfill material. So what we have to do is to control settlement, we introduce the layer of geogrid. So basically this GBI is the base isolated layer. Base isolation was our target application for this project. That means if you have a sand rubber tire mixture here, that layer, we expect that it will dissipate the vibration energy. To control the base static settlement, we introduced geogrid. Now we see that actually with introduced geogrid, in fact, with introduction of the double geogrid, we could able to increase the bearing capacity, reduce the settlement quite significantly. So same thing, we did it in numerically and we got quite adequate or acceptable range of results. And we are happy that with this sand rubber tire mixture with the geogrid can be a viable option which can control the static settlement as well as it will reduce the dynamic response or dynamic or seismic settlement of the foundation system. Now, people may ask, what about the liquefaction problem of this kind of material? Because it's a very small, tiny size, and if it is saturated, definitely there is a liquefaction hazard happens. So we use a relatively loose sand, I think about less than 40% of relative density, and we apply that same level of CSR, the stress controlled liquefaction cyclic triaxial testing, and we saw that sand is liquefying quite easily with I remember it is hardly 40 number of cycles less than that. Whereas we applied that, we replaced the 30% sand and 70% rubber, and we have seen that this liquefaction hazard can be reduced very significantly. In fact, we have cycled it with a same level of CSR and then 1.5 times the level of CSR for about almost 100 to 200 cycles. But we see that still the effective confining stress is not becoming zero. So we are not seeing that typical butterfly stress path which we generally see for a liquefiable soil. But of course, here you have to see that it's a 70% rubber, which I feel that with static settlement, this will be an issue. But this study, we are liquefaction analysis, but we are still undergone, and still we are doing it. But one of the things is I want to highlight here is it shows that a very positive liquefaction mitigation effect. So to summarize the thing, what lies in future? I stopped with that idea of what lies in future. In fact, if you ask me that the proposed models are working fine, but there are scopes to improve them. This is a total stress model essentially, where pore pressures are not, or I would say indirectly modeled. Hence, we may not be able to do a more realistic couple analysis, which is required for most of the advanced soil structure interaction problem. These models are simple enough to cater most, but they lack strict physical basis. What do you mean by physical basis? Because these models are mostly phenomenological. It's not starting from the physics. It's not like a, for example, it's not like a Camp-Clay model where we start from the energy balancing. So in case we have to come up with a rigorous model, where is the challenge? And that will be the what for the future. And we have seen the comparisons, or we have seen the performances of these models of behaviors in a holistic manner. But how about the model behavior at the interfaces? How about the micro behavior? How this micro performance, or like just now I said, how the sand particles interaction with the rubber influences the cyclic behavior. These are the issues which would like to address. I mean, this gathering, some of the youngsters are there, they can take this as their future research. There are a lot of scope in this area. So if you please want to study more, I mean, because I've given a glimpse, there are some papers which we published last few years. So please refer to that. It's there in the ResearchGate, it's there in the Google Scholar. If you couldn't able to download, please write to me. I will be happy to share. Thank you.
Yeah, excellent. You have taken perfect. Timing is right hand. Thank you, sir. Thank you very much.
Thank you.
Very nice, informative lecture. And Professor Arvind, yeah, you can just summarize and you can go to the question.
Okay, so thank you, Professor Banerjee, for your nice enlightening lecture. And as one of the punchline which you have mentioned, I would really reciprocate that after doing all these things, developing a model is extremely difficult, especially when we come to the cyclic loading phenomenon. But what to do? That is our target, as you rightly mentioned, for us and all the listeners who are hearing. And I hope it infuses some enthusiasm from the topic, from the challenges which you have mentioned, and people take it up in a more aggressive and enthusiastic manner. So thank you all. Thank you for a very nice and enlightening lecture. And with that, I thank you on the behalf of the organizers as well.
Thank you.